Hi, I'm going to talk about the optimization of scoring rules. My name is Yifan Wu. This is my joint work with Jason Hartline, Yingkai Li, and Liren Shan. We are from Northwestern University. I will introduce our motivation by an example of peer grading. One question in peer grading is how to incentivize effort. Suppose there is a peer grader who has one assignment to grade, and on that assignment, she has n criterion for grading, maybe correctness, clarity, handwriting. The peer has binary action space. For example, she can choose not to look at the assignment. That is, she is not exerting any effort. In this case, she only has prior knowledge about the quality of the assignment. Her belief distribution is with probability 1/2 bad or good on each of the criteria. Otherwise, if the peer chooses to look at the assignment, that is, she is exerting an effort, she will have an updated posterior belief distribution. That is, she is learning the truth with probability 1/2n IID on each of the criteria. And the peer can report the mean R of her belief. Here, R is an n-dimensional vector. On each dimension, it indicates the mean on that dimension, which is the probability of being good on that criteria. And the TA reveals the truth, theta. Theta is an n-dimensional vector of bad and good. By comparing the peer's report and the TA's revealed truth, the peer can get a score in 0 and 1. And here is one very commonly used scoring rule, the separate quadratic scoring rule. By quadratic scoring, it means giving the score by the quadratic difference between the peer's report and the TA's revealed truth. By separate, it means giving a separate score on each of the dimension and sum across the dimensions. So we can calculate the expected score for the peer. If the peer is not exerting any effort, she is reporting 1/2 on each of the dimension, and the realized state, that is the TA's revealed truth, is either 0 or 1, and the expected score is 3/4. If the peer is exerting an effort, the expected score is the probability of learning the truth times the highest score, plus the probability of not learning the truth times 3/4, which is the score for reporting 1/2. And the total expected score will be 3/4 plus 1/8n. The incentive given by a scoring rule is the increase in expected score by exerting an effort. So the separate quadratic scoring rule is giving an incentive of 1/8n. So here's the problem. Suppose we have a lot of criterion for the peer to grade. That is, when n is very large, this incentive is very small. So the peer may not want to exert an effort. Maybe she only wants to report her prior knowledge and having a very high score, high expected score. Even if we use the separate optimal scoring, that is, we give separate scores across the dimensions and sum together, but we use the optimal one, the incentive is still as small as 1/2n. In our paper, we propose an optimal scoring rule that can give a constant incentive. So scoring rules are used for incentivizing forecasts and evaluations. The existing literature mainly focused on the properness of scoring rules, that is, for the scoring rule to incentivize truthful reports. In our paper, we focus on the incentivization of effort while being proper. So our problem is written as the optimization of proper scoring rules. Here's the results overview. In our paper, we propose a framework for optimizing scoring rules. We characterize single-dimensional optimal scoring rule. By single-dimensional, we mean when the agent's report has only one dimension. we propose a novel approximately optimal scoring rule for the multidimensional problem. We also show some commonly used scoring rules, such as the separate scoring rule. In the opening example, we show they are far from optimal. Here's the model of our problem. So our problem is written as maximizing the expected gain in score of exerting an effort. In our model, there is a state space theta, which is an n-dimensional real-valued subspace. For example, theta may be n-dimensional space over bad and good, or equivalently 0 and 1. And the agent has a belief distribution G, which is a distribution over the state space. We focus on eliciting the mean, the marginal mean of the agent's belief distribution, let it be mu of G. The report space is hence R, which is the convex hull of the state space, which is also an n-dimensional real-value subspace. The agent has binary strategy space. If the agent is not exerting any effort, the agent's belief distribution is simply the prior distribution, which is D. If the agent chooses to exert an effort, she will have a posterior belief distribution, let it be G. We assume the agent is doing Bayesian updating, so there will be randomness in Bayesian updating, and there will be a distribution over posterior distributions. So we let distribution over posterior means be f of R. And after the state theta is realized, the agent can get a score S, which is a mapping from her report times the state to a real valued score. This is the definition of proper scoring rule. We say a scoring rule S is proper for the mean if, when the agent believes the distribution, the theta follows distribution G. On the left-hand side, this is the score of the agent reporting the marginal mean of her belief distribution G. So we say this is the truthful score. And on the right-hand side, this is the score of the agent reporting something else, R, in the report space. And this is the non-truthful score. We take expectation on both sides. So this expectation is taken over theta when theta follows the agent's belief distribution. This is to say, from the agent's perspective, the expected score of being truthful is at least the expected score of being non-truthful. So the agent will prefer to be truthful. So our problem has two constraints. The first one is the scoring rule S is proper for eliciting the mean. And then the scoring rule should be ex-post bounded, which means we only want to give, for example, the peer a score that is bounded in an interval, say 0 and 1. And this is the mathematical definition of our problem. So our program is written as maximizing the expected difference between reporting the marginal mean of posterior and reporting the marginal mean of the prior. And two constraints. First, S should be proper for eliciting the mean. And second, S should be bounded in 0 and 1. This is the outline of this talk. I will first start by introducing some preliminary knowledge of proper scoring rules. I will introduce the characterization of properness for mean. And then I will talk about our single-dimensional problem. I will introduce the optimal scoring rule for single-dimensional problem. And I will go to multidimensional problem. I will introduce the approximately optimal scoring rule for multidimensional problem. And I will compare the separate scoring rule to optimal scoring rule. In the last part, I will introduce some related work and conclusion. First, the preliminary. Here is the characterization of proper scoring rules for mean. In our paper, it is sufficient to consider the set of canonical scoring rules. We say a scoring rule is a canonical scoring rule if it is defined by a convex utility function U, which is a convex function over the report space R, and a set of subgradients C, which is subgradients of the convex function U, and the function kappa, which only depends on the realized state theta. And the scoring rule has the following form. here. Notice that if from the agent's perspective, the distribution over the state theta is fixed, the expectation of score only depends on U and C, does not depend on kappa. So this kappa function does not affect the truthfulness of the score. And when the agent is reporting truthfully, the expectation of score has the form of the convex utility function U at the report mu G plus some expectation of the function kappa. With this, we can simplify our objective to be of the following form. So this is taking expectation with the convex utility function. The expectation is taken over the posteriors. So here F is the distribution over posterior means, and minus the utility at the prior point. So this kappa function does not affect the truthness and also does not affect our objective. So we can omit kappa and think of U as the expected truthful utility in this problem. Here is one geometric interpretation of this scoring rule. It shows why this scoring rule is truthful. So in this plot, in black solid line, we plot a convex function U. Suppose the agent's belief distribution is theta, that is with probability theta being state 1. If the agent reports truthfully, her utility will be U of theta. But now suppose the agent wants to be non-truthful and deviate to report something else, say R. By this characterization, the score will be on this black dashed line at theta. And we see the value here on dashed line at theta is lower than the value U theta. So the agent will prefer to report her true belief theta, that is, she's being truthful, and this scoring rule is proper. With this characterization, we can look at our single-dimensional problem. Recall that our optimization problem has the form of expected difference in utility of reporting the posterior and reporting the prior. So in this plot, this is any arbitrary utility function U, convex utility function. We will show the optimal utility function has the form of V-shaped function. We define a function U to be V-shaped at mu d if it is linear on both sides of mu d. In this plot, in black solid line, we construct a new V-shaped function. So this function is constructed by having the same value at mu d, which is the prior mean, and also having the same value at two extreme points, 0 and 1. So we can see the difference in utility is the difference in utility of this V-shaped function exceeds the difference of the original function, which means this V-shaped utility function in black solid line weakly increases the objective. And also we can show if the original utility function in dashed line satisfies the score boundedness constraint, the new V-shaped utility function also satisfies the boundedness constraint. So our theorem says for any distribution F over posterior means, the optimal solution has the optimal scoring rule has a utility function that is V-shaped at mu d. It means to implement this optimal scoring rule, the principle simply offers a binary choice to the agent, that is letting the agent choose if she is on the left or right side of the prior belief mu d. And to implement this scoring rule, the principle only needs the knowledge of the prior mean mu d. In our paper, we have some comparison to some widely adopted scoring rules. For example, the quadratic and spherical scoring rule. We show they are not optimal. Instead, our optimal V-shaped scoring rule is not well studied. Then for the multidimensional problem, we show our approximately optimal scoring rule. We define a scoring rule S is max over separate if there are single-dimensional scoring rules S1 to Sn with utility function U1 to Un, such that the final score S is given by the dimension that has the highest expected utility. And for this max over separate scoring rule S to be bounded and proper, on any dimension I, the single-dimensional scoring rule Si should be bounded and proper. To implement this max over separate scoring rule, the principal can use the choose and report mechanism. That is, the principal posts single-dimensional scoring rules on each dimension of the assignments, and the agent chooses her favorite dimension to report. Here is the commonly used separate scoring rule. We say a scoring rule S is a separate scoring rule if there are single-dimensional scoring rules S1 to Sn, such that the final score S is given by the sum across the score on each of the dimensions. Recall in our opening example, we have seen that the optimal separate scoring rule can only give an incentive 1 over 2n, which is vanishing to 0. But in this case, our max over separate scoring rule can give a constant incentive. This shows us the approximation ratio of the separate scoring rule can be as large as the order of n. Our theorem says the optimal max over separate scoring rule achieves at least 1/8 of the optimal objective value. This is to say the optimal max over separate scoring rule is a constant approximation. Note that the optimal max over separate scoring rule has a high dimensional V-shaped utility function U. So to implement this scoring rule, the principal also only needs the knowledge of the prior mean. And it means the most surprising dimension gets scored. By most surprising, we mean the dimension that deviates the furthest from the prior mean. The intuition behind the optimality is that linking decision is better for the principal. So linking decision means letting the agent make a decision, make a report based on all the information she has across the dimensions, not making separate decisions on any single dimension. And this has been observed in previous auction literature. In the last section, I will talk about some related work and conclusion. Previously, there are some work characterizing properness of scoring rule. For example, for eliciting the full distribution, eliciting the mean, and set of elicitable properties. So these are the characterization of the properness. This work does not consider the incentivization of effort. OSPAD 98 consider maximizing effort with quadratic scoring rules. However, in our paper, we consider maximizing effort with the set of all scoring rules. There is an independent work, Neyman, Norev, and Weinberg maximize effort in a binary state model and with costly samples. So in our paper, we don't have assumptions on the cost of obtaining a sample. Instead, we consider maximizing the incentive given to the agent. Also, we consider a general state model and under a binary effort level model. There are a lot of follow-ups of our work. For example, Chen and Yu consider the optimization of max-min objective without knowledge about prior and signal. Kong considered optimization of peer prediction mechanisms. We also have another follow-up work. We consider maximizing effort when the effort model is also multidimensional. To conclude, in this paper, we show a framework for optimizing scoring rules. We characterize single-dimensional optimal scoring rule. We also propose an approximately optimal scoring rule for the multidimensional problem. And we show some commonly used scoring rules, for example, the quadratic scoring rule in single-dimensional problem and the separate scoring rule in multidimensional problem. We show they are far from optimal. Thank you for listening.